This is the pre-lecture video for the first half of Chapter 7. This chapter deals with the periodic nature of the elements. Last chapter we discussed the electronic structure of atoms in terms of their electron configurations. This chapter we will see from left to right across the periodic table how the nucleus plays a role in determining the properties of a given atom. So the periodic table was developed by Dmitri Mendeleev and Lothar Meyer. They kind of both came to an independent and similar set of conclusions that the atoms could be grouped by order of increasing mass and also by grouping them into properties of elements that share similar trends, such as the alkali metals, which share the trend that they all form +1 cations, the alkaline all form +2 cations, your halogens form -1 ions, and the noble gases are all stable. So they also were using some of the elements at the time that were known around the time of the development of the periodic table, roughly in the mid-1800s. Some of the elements were known, but certainly not all of the elements. Some elements were only discovered recently. Some of the earliest discovered elements were things like iron, copper, silver, gold, mercury, carbon, silicon. And then some of the elements that came next were like zinc and platinum and phosphorus, arsenic, antimony, bismuth. And then some of the remaining major elements were then found, like nitrogen, oxygen, fluorine, the rest of the halogens, some of your smaller alkali metals, your alkaline metals. And then as you can see, as time goes on, some of the larger elements are filled in. And then continuing on to more current times, we're discovering some of these really large unstable atoms, which are only able to be really discovered and characterized through bombarding something like uranium, or a relatively large atom, because that's the largest natural occurring element on the periodic table. So all these other elements have to somehow be synthesized through some complex nuclear pathways. Some of those pathways are discussed later in chapter, I believe it's 23 in our textbook on nuclear chemistry. So in the mid to late 1800s, as Mendeleev is making some of the predictions on the periodic table, the element below silicon was not known to be discovered yet, so they called it below silicon or ecosilicon. And they were able to predict things like the molecular weight of that compound or of that element, the density, and some of the other properties, just kind of going on some of the other elements and their top to bottom trends. So they were able to use the idea and further the ideas of the periodic nature of matter to actually help predict some of the properties of new elements. And then once those elements are discovered, you can then make some comparisons and see that, generally speaking, a lot of these predictions are kind of matching up, that you're getting roughly a good approximation of the atomic weight, the density, and some of the other properties of the atom or of the element. So Mendeleev made his table on the basis of atomic masses. Atomic weights weren't yet known, the atomic numbers weren't yet known. So the ideas of the proton and the neutron and the discovery of those subatomic particles is still about 50 years removed from when Mendeleev is putting together this first periodic table. So about 35 years later, the nuclear atom was discovered, and then about 15 years after that, you have the actual discovery of the neutron. And in the middle of that time, you then had some of the fundamental experiments, like Moseley developed the concept of atomic numbers by bombarding different atoms with high energy electrons and then seeing that each of the atoms displayed a unique X-ray pattern. And we're not going to talk about what these patterns look like, but what the pattern was found to be of a multiple of the number of neutrons that the atom contained, or of the number of protons that each of the atoms contained. And so this furnished and led to the atomic number of each of the elements. And then you could reconstruct the table, go back through there. There was an element or two that was actually misplaced by order of mass, because the elements actually don't increase in mass in every case, but they do increase by the number of protons in every case. The atomic number, the elements go in order of the protons in the nucleus, not exactly the masses. So this ended up being not an entirely correct table, and then some corrections were made once Moseley made some of his discoveries. So then one of the primary trends from left to right that's actually responsible for some of the periodic nature of our elements, and there is quite a bit of change as you go from left to right. If you start from the left side in terms of, say, lithium, and then go across to, say, fluorine, and eventually get to neon, you go from having a metal to having some metalloids in the middle, like boron is probably best described as being a metalloid. Then you have like carbon, which is a solid at room temperature, but totally different in its properties than something like lithium metal. Like carbon doesn't dissolve and make +1 cations like lithium does. And then you get, fluorine and neon. Fluorine's forming minus ions and neon's a stable gas. So, you get a totally different set of properties from left to right. And the main property of the atom that's going to be responsible for those differences is the effective nuclear charge of the atom. And what the effective charge is it's the charge that the valence electrons are experiencing within an atom. So many of the properties depend on the attractions between the valence electrons and the nucleus. How much of that nuclear charge makes it all the way out to the valence electrons. So the electrons are both attracted to the nucleus and repelled by other electrons. So this example here is looking at sodium. So let's recall sodium is a 1s2, 2s2, 2p6, 3s1. So if we're thinking of this one electron in a 3s orbital, we got an 11 plus nuclear charge, because sodium has a Z, the atomic number of sodium is 11, so we got 11 protons in the nucleus. Now this negative charge is not experiencing that full 11 plus charge because there's all these electrons in the middle. So you have like the 1s electrons, there's 2 of them, you have the 2s, you have the 2p shell electrons with 6 electrons. So you're only seeing about a net +1. You can almost think of this inner core only leaves behind about a +1 charge. So you have an 11 plus charge that's dampened out by about the 10 electrons of the core, leaving behind only about a charge of +1 that outer electron can experience. And so then if you go, okay, well, what about magnesium? Magnesium then just has a second electron, still 10 electrons. It's going to experience a +2 charge. So if you're looking at like sodium to magnesium, not sodium plus, just sodium as a metal, sodium no electrons compared to magnesium, the valence electron in sodium is experiencing a +1 charge. That of magnesium is experiencing about a +2 charge. And then the s orbitals and the p orbitals are really not that much different in size. So they're not really screening nuclear charge from each other. So if you go all the way across to something like chlorine, chlorine's experiencing a charge about +7 nuclear charge units. Because it still has the core of 10, it now has, though, a Z of 17. So it has the exact same core as sodium and magnesium, meaning that they have the exact same neon core of 10 electrons. And so the charge that's left over for the valence electrons to experience is much higher for the case of chlorine. Now that plays a very important role in terms of how strongly those valence electrons are held onto by chlorine. So chlorine's valence electrons are experiencing a much higher positive charge, so that the atom's going to require a much greater energy to remove those electrons. And then in fact, chlorine's going to have a much easier time actually absorbing an electron to go to Cl-. So sodium is going to be situated in such a way that it won't take that much energy for it to lose an electron. Chlorine will actually gain energy by absorbing an electron. And then once you make a sodium plus and a Cl-, we'll see this come together in chapter 8 later on, then you end up with the electrostatic attraction in your ionic compound, where that electrostatic attraction leads to a very strong force of attraction, allowing something like NaCl to be an important type of compound that results when sodium and chlorine interact with each other. And so the left to right trend for effective nuclear charge is that it's increasing because the core is remaining constant. And then the nuclear charge is increasing so that we're seeing a much higher nuclear charge as you go from left to right. Now, as soon as you get to neon, you end up with an atom that would have a low likeliness of losing an electron because it's going to have its outer electrons experiencing a +8 charge, and then nowhere else to put a new electron. So no way to make neon minus easily. So we're going to be kind of stuck with neon as a stable gas, where it's not going to participate in sharing or adding or losing electrons with other atoms. So effective nuclear charge, the effective charge experienced by something like a valence electron, can be calculated by taking the nuclear charge and then minus the shielding or the screening factor. Now the screening factor, S, is approximately equal to the number of core electrons. And that's not going to entirely be correct, but it's a pretty good approximation, meaning as you go from left to right, you get an increase in your effective nuclear charge across a period. That's from left to right. So from left to right, you get an increase because the core electrons are constant. Your effective charge then increases because the Z is increasing, and that S, the core electrons from left to right, is mostly the same. Let's look at a chart to kind of show us a couple things. One is actually showing us the effective charge. You can calculate the effective charge that any of the electrons experience. It's not necessarily the valence electrons charge that they experience. Most of the time, though, that's how we discuss and use effective nuclear charge, is to compare the valence electron's attraction to the nucleus. But let's think of something like lithium. So lithium has a 1s2, so you can think of 2 electrons spinning around the nucleus, a 3 plus, and then you have a 2s with 1 electron. So you have a 1s2, 2s2. So then you can think, okay, what charge do the 1s electrons experience within something like lithium? Well, it's going to be about the full positive charge. You know, that those 1s electrons are experiencing the full nuclear charge. If you go all the way out to argon, it's not quite 16, but it's very close to equal to 16, meaning that the outer electrons in the atom aren't really screening the inner electrons. It's kind of the opposite. The inner electrons are absorbing the charge and preventing the outer electrons from experiencing that charge. And so if you're looking at lithium, only about a +1 is making it through to the outer 2s1 electron for it to be attracted to the nucleus. If you look at something like beryllium, then it's going to be about a +2 charge making it out to its valence electrons, and etc. And so then if you approximate S as being directly equal to the number of core electrons, like our approximation is suggesting, that's the green curve. And so that shows that from left to right, you'd go from a +1 nuclear charge on lithium all the way to neon having a +8 effective nuclear charge. And if you jump down to sodium across to chlorine and then to argon, then you got the exact same +1 to +8. Now what you can see when you look at the blue curve is it's not exactly so much exactly equal to the number of core electrons, but you get the same trend. You get the same general increase from left to right in the effective nuclear charge, and it's just a little bit off. And one of the things that ends up happening, if you go from like lithium to sodium, it goes up just a little bit from top to bottom. Okay, so you get a slight increase as you go down a group. So as you go from top to bottom, the effective nuclear charge to the outer valence electron is increasing slightly. Now what this implies is that when you start thinking of like a relatively large core, so like let's think about sodium. So if you have sodium, that the 10 electron core is not quite 10, that each of those electrons is only dampening out some relatively smaller fraction of charge. So that the screening ability of the electrons is becoming a little bit poorer as they're further away from the nucleus. If you go to something relatively big, think of something like cesium. Cesium is going to have a relatively larger effective nuclear charge because it has much larger core electrons, which won't be absorbing as much nuclear charge as the smaller core electrons do. So you get this slight increase in Z effective from top to bottom. Now what about the size of atoms? Now there's two different sizes that we can discuss. One is what we might call the non-bonding radius. One of the things that's kind of hard to characterize in terms of an atom is, how big is the atom truly? Because you have, if you picture something like carbon, you have a 6+ nuclear charge, a 1s shell, a 2s shell, a 2p shell. And then these are like distributions of where you most probably expect to find an electron. So how do you define the actual size of the atom? Well, the size of the atom kind of depends. If you would have one atom that would just bump into another atom and just bounce off, that's called the non-bonding atomic radius. And so if two atoms were to collide, it's kind of the distance that those atoms' nuclei would be just divided by 2, because no bond actually results when those atoms are bumping into each other. So you have two atoms just simply collide off each other, and then the size is being determined by how close those nuclei can get. So you see how close the nuclei can get, and you take that distance, divide by 2, and you get your non-bonding radius. Now we can also classify something called the bonding radius, since it's much easier to study bonds that actually form, if you were to take something like two hydrogen atoms bonded together and do an experiment to determine what the bond length is, let's say it's 0.74 angstrom, then you could use that, or yeah, I think that's about the bond length of H2, that if that's the bond length of H2, then the radius of each of the atoms, so if that's the bond length that separates the two nuclei, then we just simply divide that by 2, and the radius of each atom would therefore be about 0.37 angstrom. And so you can get your bonding atomic radius by cutting the bonds in half. Now the thing that ends up happening, if you think about the bonding radius, is the bonding radius of an atom should be a little bit shorter than the non-bonding atomic radius. Because the non-bonding atomic radius will be slightly larger since these atoms are going to overlap as they're making that bond. So there will be some overlap. So the bonding atomic radius should be a little bit shorter than the non-bonding atomic radius. Now this chart here is showing some of the bonding atomic radii trends. We can clearly see from left to right you get a decrease in size. Think about getting to fluorine in terms of your decrease in size. And so, and the reason why you get a slight jump up in the case of neon is because they don't form bonds. So helium, neon, argon, these are actually your non-bonding atomic radii. Since they don't form bonds, the only thing you can get for those are non-bonding radii. And something like fluorine, you're comparing like the bond and something like an F2, where the bonding atomic radius should be a little shorter than the non-bonding atomic radius. So this is why you see a decrease to fluorine, and then a slight increase back to the noble gas. But now, why do you see like lithium being bigger than something like fluorine? What explains this trend here? Well, it's that effective nuclear charge. You have that effective charge of about +1 in lithium and about +7 in fluorine. The valence electrons in fluorine can get much closer to that positive charge because it's going to pull those electrons in more closely, making fluorine be the smaller atom. Lithium, smaller positive charge, has to be a bigger atom. And then as you go from top to bottom, as you go from having, you know, like imagining as you're going from like a 1s to a 2s, and then as you're going from left to right, that these orbitals are going in closer to the nucleus, becoming smaller. Then when you get back to something like sodium, and you have then a bigger 3s orbital on top of it all, the size has to grow. So as you go from top to bottom, the size is always increasing because the next successive shell, the next successive larger orbital, the 3s orbital, always has to be larger than the 2s orbital. So like sodium's and neon 3s1, that 3s1 orbital is always going to be bigger than the 2s1 orbital in something like lithium. So we get a increase from top to bottom in size, and we get a decrease from left to right. And then we get that weird little blip where the noble gases appear to be a little bit larger, but that's just the artifact of those showing and using their non-bonding radii instead of the other elements showing the bonding atomic radii. Now what about the size of ions? So let's think about the size of ions. So now it should depend on the charge of the atom, the number of electrons, and the orbital in which the electrons reside. Now the bigger comparison here to make is starting with like lithium. If you take an electron away and go to lithium plus, you're going from a 1s2, 2s1 to a 1s2. So it probably shouldn't be so surprising that if you remove an electron from lithium, you make the atom smaller. If you remove 2 electrons from beryllium, make your stable beryllium 2+, you're going towards that noble gas helium configuration. Then of course you go to a much smaller cation. And then we'll pick up the size of why beryllium is smaller than lithium in terms of a cation in a moment. But we get some trends here, boron 3+, even smaller. Now oxygen and fluorine are going to do the opposite. They're going to add electrons. So you take oxygen, which has 8 electrons, and then you go to the neon core with 10 electrons, you're adding negatively charged particles that repel each other. Again, it shouldn't be so surprising that the size increases, and it actually increases by quite a bit. These sizes are doubling, or nearly doubling. So fluorine actually doubles in its radius as it goes to F-, just with the addition of 1 extra electron. And this is due to the electron repulsion, making those atoms then larger in size. And so fluorine would stop at F- in terms of a stable ion and not go to F2- because that would take it beyond your noble gas core. Sodium, magnesium, aluminum, losing electrons again, smaller in size than their neutral counterparts, and then increasing in size sulfur ion, sulfide ion, and chloride ion. And the same trend can be emerged from top to bottom, as you might expect that lithium to sodium to potassium to rubidium increase in size, so too do the cations. So lithium plus to sodium plus increase in size potassium, all the way up to rubidium. And then you see that trend is a very obvious and repeating trend, that from top to bottom, you get an increase in the ionic radii, just like you do in the case of the atomic radii increasing from top to bottom. So lots of trends. So we see the cations are smaller than their anions, and then anions are larger than their neutral counterpart atoms. So that's kind of summarized here, that cations are smaller than their parent atoms. So sodium plus has a smaller radius than sodium. That's because we're removing an electron. All the remaining electrons are a little bit more attracted to the nucleus, and you lose then that larger orbital that contained that 3s1 orbital. So you have the argon configuration followed by 3s1. Obviously that's going to be bigger than just the argon configuration. And then anions end up being larger due to electron configuration. So if you're comparing like oxygen, that's going to be a smaller atom than oxide ion. So oxygen is a helium core, 2s2, 2p4, add 2 more electrons, go to the neon core. Of course, you're going to increase in size as you're adding 2 more electrons, increasing the repulsions of those electrons, and hence increasing the size of the ion. So then we can compare ions across what we might call or term an isoelectronic series. So if you look at O2 minus, F minus, sodium plus, magnesium plus, aluminum 3 plus, let's think about their radii trends. Because what we can make a comparison on here is that O2 minus has 10 electrons, F minus has 10 electrons, sodium plus has 10 electrons, magnesium 2 plus has 10 electrons, and aluminum 3 plus has 3 electrons. Aluminum 0 has 13 electrons. Lose 3 electrons, you go to 10. Okay, now think about the number of protons. The effective charge, or the atomic number of oxygen, is 8, 9 for sodium, 9 for fluorine, 11 for sodium, 12 for magnesium, 13 for aluminum. That's the number of protons in the nucleus of those atoms. So if you have this core, so if you have 2 electrons and a 1s, 2 electrons and a 2s, and then 6 electrons in p orbitals, and I'll just show 3 of the 4 p electrons, then think about the effect that these negative electrons in these orbitals are going to have if we go from something like an 8 plus charge all the way up to like a 13 plus charge. If you increase to 13 plus, all those negative particles are going to be attracted in much closer to the nucleus. So aluminum ends up being the smallest, then the 12 protons, then magnesium 2 plus, then sodium, then fluorine, then oxygen in terms of their ions. Now think about the trend if we just said to rank the size of like O versus F versus say sodium without the charges. So if you're saying, okay, rank these atoms here in terms of their size, fluorine is further to the left, it's going to be the smallest, oxygen is going to be bigger, and then oxygen is bigger than something like lithium, and lithium is going to be certainly smaller than sodium. So if you kind of go from this analogy here, fluorine is smaller than oxygen. We know oxygen is smaller than lithium, and we know lithium is smaller than sodium. So sodium has to be the biggest, then oxygen, then fluorine. But this is when you're comparing 11 electrons in sodium, 8 electrons in oxygen, 9 electrons in fluorine with their respective nuclear charges. So then if you go to the cation, then sodium goes smaller, and it even goes even smaller than O2 minus and F2 minus because they're growing bigger. So remember that oxygen's going bigger, fluorine's growing bigger, and then sodium's going smaller, so you get kind of a switch here, and that sodium plus ends up being the smallest, then F minus, then O2 minus in terms of the biggest, because you have the fewest protons, and these all have the exact same number of electrons. These all have 10 electrons, and then oxygen has the least number of protons, so it ends up being the largest. So we can compare an isoelectronic series. Those are ions that have the exact same number of electrons, and compare their sizes very easily. Their sizes depend on the number of protons. More positive particles makes that ion smaller. So let's do a quick summary. We have 2 trends so far. We have the effective nuclear charge for valence electrons, if we're considering those for an atom. From left to right, we get an increase in the effective nuclear charge because the core electrons are constant and Z increases. So the Z is increasing, and the core is constant. And then from top to bottom, we get a slight increase because the core electrons become poor screeners of charge as their size increases. And then the effective nuclear charge, the atomic radius of atoms, so the size of atoms, we get from left to right a decrease in size, and that's because of the increase in the effective nuclear charge. So this is increasing because of the Z effective trend. And then from top to bottom, we get an increase in size, and that's due to electron repulsion, or just the idea that each shell is larger. So each successive shell increase in size. So like a 3s orbital is going to be bigger than a 2s orbital. So sodium is bigger than lithium. Okay, let's move on to another trend, that of the ionization energy. So the ionization energy is the minimum energy required to remove an electron from the ground state of what is technically a gaseous atom, or ion. Now this just means when we're talking about the ionization energy of sodium, going to sodium plus an electron, the ionization energy, we'll call this I1, the first electron to remove from sodium, is about 496 kJs. So 496 kJs per mole. And so that this ionization energy, and all the ones you see in this chapter, are specifically for a gaseous atom. And that'll apply a little bit to the next chapter on a topic we'll talk about later. But it gives us an idea for sodium how tightly the sodium the sodium nucleus is holding on to this electron. And then we can kind of compare a different atom and see if this ionization energy is greater or lower to get a sense of what that means in terms of how tightly that valence electron was held onto in terms of the energy it takes to remove. So the first ionization energy is the energy that's required to remove the first electron. The second ionization energy is the energy that's required to move the second electron, and then it would be from the next, let's just take an example of magnesium. So magnesium's first ionization energy would be magnesium gas going to magnesium plus gas plus an electron. This would be the I1 of magnesium. The ionization energy 2 would be the plus cation losing a second electron. Okay, so it's magnesium plus losing the electron to go to magnesium 2 plus. And what I'm really hoping to point out here is that the I2 is not the energy required to remove both of the first two electrons, but just the energy required to remove the second electron from the result of the first ionization, so from magnesium plus. And so if you were to add up I1 plus I2, then that would be the energy to go from magnesium to magnesium 2 plus 2 electrons. Let's take a look at some trends for the elements in the periodic table. So what we have here are the ionization energies from table 7.2 for the third row of the periodic table, so for sodium across to argon. So sodium's I1 is 496. The energy it takes to remove the next electron is actually very high because that's removing a core electron. So this is removing of one of those core electrons. Now theoretically, not even theoretically, experimentally, you can truly keep removing electrons. And this energy will keep going up and up and up as you kind of continue. So you can develop experiments that can continue to remove electrons from ions. It's going to take a tremendous amount of energy though. Now let's look at magnesium. The energy required to remove the first electron is higher than sodium. Why might that be the case? Why might this energy have gone up? Well, it's because the Z effective has gone up. So the effective nuclear charge of sodium is about +1. It's about +2 for magnesium. So you have the electrons, the outer valence electrons of magnesium experiencing a greater charge, hence harder to remove them. And then the second electron to remove from magnesium takes even more energy. So we get an increase to remove the second electron because now there's just one electron left over, and it's being pulled away from that same effective nuclear charge. So we get an increase in the effective nuclear charge. We also have removed an electron that was being repelled by this electron. So like the first electron removed had some electron repulsions with the electron that remains, so then removing the remaining electron takes even more energy. Okay, then when you finally get to the third electron for magnesium, you get a big increase. So you about doubled from I1 to I2, then you about go up by about a factor of 5 to 10 when you start removing the core electron. So you get a big jump, a much bigger jump when you're removing a core electron. So aluminum, this is an interesting trend. We'll talk about this in a few moments, but aluminum actually drops from, in terms of its ionization energy. So we'll have to see why that's the case. The effective charge on aluminum is higher. It's going to be due to the fact that that electron is being removed from a larger 2p orbital compared to the relatively smaller 2s orbital of magnesium. So it's going to have to do to the orbital nature of these electrons. But so it's 578 for the first. It's greater than for the second electron to be removed, and even greater for the third. And then as soon as you go to aluminum 4+, that comes from the fourth electron would be removing a core electron, so you get that big increase in that ionization energy. Silicon increases, phosphorus increases in the first ionization. Their successive ionizations are all higher. One of the things that you can always see is that I2 is always greater than I1. This is for all atoms. And then you get that big jump for a core electron removal. So you get a much bigger increase when you start removing core electrons. Okay, we get all the way down to argon, and even like phosphorus to sulfur. We'll have to talk about this in a minute too, on why there's not an increase to sulfur. It has to do with the electron configuration of sulfur compared to phosphorus. So we'll take a look at that in a moment, but then an increase to chlorine, then an increase to argon. So we get a general trend that the ionization energy is increasing from left to right. And then there's just a periodic inconsistency. And we'll see that it's periodic here in a minute, meaning that when you look at other groups of the periodic table, you get kind of this similar lack of an increase in the exact same spot. So there's a periodic inconsistency. Okay, so let's summarize. So the I1 generally increases across a period. We had that periodic inconsistency that we need to talk about. I1 actually decreases as you go down a group. So as you go from like lithium to sodium to potassium, you're taking this outer electron and moving it into a larger orbital. So as you have that valence electron in potassium being further away, it's going to be a little bit easier to remove that larger valence electron from something like potassium. So you get a slight decrease in the ionization energy when you go from top to bottom down a group. The S and the P block show a pretty big range of changes in ionization energy. The D block, we'll see in a moment that it actually shows just a very slow, but yet still a slight increase from left to right. Okay, so let's take a look at the atoms from left to right. So we get big increase, then the decrease, then an increase, decrease, increase. So we get that top to bottom, an increase, and then a decrease, and then increase, decrease, increase. The same thing, increase, and then we go across the D's, generally an increase. There's some blips with that we're not going to get into. And then you get a drop, and then increase, drop, increase. Okay, so again, just pointing out that this is periodic, that you get the drop, relatively flat across the D's, and then you get a drop, increase, drop, increase. Okay, so why do we get the drops for the 2p1s and the 2p4 configurations, or the MP2s? NP1 and the NP4 configurations show that periodic inconsistency. Let's take a look at why that might be the case. Okay, so I'm going to try to build this example. I'll probably do this in class too, because this is a little bit confusing. Let's take a look as we go across from lithium across to fluorine over to neon. And we'll see how far we have to go here. Now, what I was to think about is a little bit about Bohr model, of just kind of writing these relative energy levels. And that for lithium, we're thinking of its 1s. I'm going to think about just the valence. So I'm thinking about the relative energy of the 2s. So we have one electron in a 2s orbital. And so then from the Bohr model, you might remember you can go up to like 3, 4, 5. Eventually you're getting to some infinity state where n is equal to infinity. You can then ionize. So n equals infinity, this is our ionization. So this is the atom plus, and then plus the electron removed. And so you can think that this difference here is roughly corresponding to your ionization energy. So then when you think of moving to beryllium, you can think, well, what effect does beryllium's nucleus have on the 2s orbital? What you're doing is you're moving that orbital closer to the nucleus, and then you're putting 2 electrons in it. So you're ending up with a more stable orbital, but you're not like changing where infinity is. So this line is meant to be just straight across. So this difference here is certainly going to be greater. So that this I here is going to increase compared to that of lithium. Okay, so this is helping us see that it's going to take a greater energy to remove what is like a more stabilized 2s orbital, more stabilized because it's closer in on that net 2 plus approximate effective nuclear charge, assuming that the atom's core electrons of 2 are just being subtracted off of their z's. Okay, so the big difference here now, I want to think about to boron. Think about the 2s shell for boron. It's down here. It's more stable, closer to a 3 plus charge. If we were trying to remove those electrons from boron, it would take more energy. So the ionization energy of the 2s electrons from boron would take more energy, but those aren't the valence electrons. The valence electrons are higher in energy. Now it's from a 2p subshell. And so it just stands to reason that the 2p subshell, slightly larger orbital, slightly further away from the nucleus, it's kind of just like not an apple-to-apple comparison to compare the ionization energy of boron to that of beryllium. Now, this is the part where this is kind of confusing. The whole idea of ionization energy is only really being presented as almost like a proof of concept of an increase in charge from left to right should correspond to an increase in the energy it takes to remove an electron. And then it just is that the electrons from left to right aren't exactly the same. They're not in the exact same type of orbitals. So you get a smaller I1. So the I1 goes a little bit smaller because the 2p orbital is just simply higher in energy. A slightly larger orbital is one way to think of that. And so then let me draw this just a little bit smaller. Let me just rewrite this so I can try to get some of the other elements on this chart. So the I1 here will drop for boron compared to beryllium simply because the 2p orbital is higher in energy than the 2s. And so then you can think, okay, what about carbon comes next? Carbon should be in a slightly more stable 2p orbital because the 2p orbital is now closer to that nucleus of carbon. We now have a +4 charge that nucleus is getting closer towards, so the 2p orbital should drop a little bit, so this I1 should go back to generally following that increasing trend. Same thing if we go to nitrogen. Okay, so nitrogen, 3 electrons, the 2s orbital closer to the nucleus as well. So all these ionization energies would increase. The I1 here should increase. Okay, now the last example I probably have to do is oxygen, because when we think now of oxygen compared to the 2p orbitals, when we spin pair an electron, that adds some destabilization. And it actually leads to the 2p orbitals no longer being what we would call degenerate, not exactly equal. So as soon as you have one orbital that has 2 electrons in it, and then one that has 2 electrons in it, the one with 2 electrons in it is slightly destabilized due to the spin pairing. So the spin pairing, those electrons repel each other more, so we get spin repulsions of those 2 electrons, destabilizes the orbital, it kicks that I1 back upward. And then if you continue on to then have 2 orbitals that look just like this, they're closer to the nucleus in fluorine, and they're closer to the nucleus in something like neon. So when you go to neon and have all 3 of these, you get the 2s orbitals always decreasing in energy. So if you compare fluorine, you get 2 and then 1. So the idea would be that oxygen destabilizes one of the 2p orbitals due to spin pairing, and then fluorine destabilizes 2, but they're more stabilized than the one of oxygen simply because the nuclear charge of oxygen to fluorine increases. An even bigger increase to neon should then kick the I1 of neon to be the greatest within the chart. Okay, so relatively confusing perhaps, but the idea here is that the 2s orbital is always going closer to the nucleus. It would require a greater amount of energy from left to right with no periodic inconsistency to remove the 2s electron. But the 2p orbital grows a little bit higher in energy, so we get a decrease in the ionization energy for boron from what we might expect. And then we get a decrease in the ionization energy for oxygen due to spin pairing in the 2p orbital. And most of this is kind of a distraction because the whole idea of ionization energy wasn't to get into these little nuanced details. But if we really want to understand the left to right trend on why it has this periodic inconsistency, we can really make sense of it with just a very rudimentary understanding of electron configurations and the idea that the 2p orbital is slightly destabilized compared to the 2s orbital, higher in energy, and then likewise putting 2 electrons into that orbital destabilizes that orbital as well. Okay, so let's compare a couple things. So let's look at the electron configurations of ions. We talked about electron configurations of atoms back in chapter 6, but we're going to continue on to ions here in chapter 7. So we talk about ions here within chapter 7. So cations, the electrons are lost from the highest energy level, the largest orbital. So electrons are going to go from the largest orbital first. So the largest orbital electrons are removed first. So one of the ideas is if you want to come up with a configuration for calcium 2+, think of calcium 0 first. Same thing for iron. Think about iron 0 and its configuration. So the configuration of calcium 0 would be argon, precedes it, and then it's a 4s2. And then iron 0 would be a 4s2, 3d6, then the same thing. Okay, so for calcium, we're going to lose the largest electrons first. So those are the largest electrons will be in the orbital with the highest n value, which also has the greatest L value. So what that means is the n equals 4, the 4s orbital, the largest electrons of calcium, they're lost. So calcium 2+'s configuration is just simply the exact same as that of argon. So iron 2+, its configuration, we want to go and think about iron 0 first and think which one of these orbitals is bigger, 4s or 3d. So it's the largest n of the largest L. The outermost shell is larger, that's why it has a larger n value. N relates to size. So the 3d is smaller than the 4s because it's filling in the n equals 3 space. The 4 is filling into the n equals 4 space. Okay, and so we're going to lose the 4s2 electrons first. So the configuration of iron 2+, this will be argon 3d6. Okay, now once you remove the 4s electrons, you need to remove one more electron to go to iron 3+. What electron comes next? So here are the first two that are removed. Then you got to go to the greatest n with the greatest L, the largest orbital. So the largest orbital for iron 2+, the next one would be the 3d. So the 3d6 electrons come next. We take just one of those away. So the configuration of iron 3+ would be argon 3d5. Now, sometimes people think that this is some kind of anomaly. No, this is the rule. So for every single cation, this is how we come up with their configurations. Let's go back to zinc for a minute. So zinc, we talked a little bit about its valence count, how it only has 2 valence electrons. The d electrons don't count. The configuration of zinc 2+ wouldn't make sense if we're losing the d electrons. Those are actually pretty tightly held onto. We're going to lose the larger 4s. So zinc 2+ configuration, argon 3d10. And again, this isn't some kind of anomaly. This is just the rule for cations. Okay, so for anions, electrons are just added to the parent atoms in the same order you would expect. And so the configuration of oxygen 2-, so oxygen without the 2- would be a 1s2, 2s2, 2p4, and we just need to add 2 electrons, go to 6. And 3- comes up with the same configuration. And then argon, let's think about argon with a minus charge. So the configuration of argon would be like neon's configuration, 3s2, 3p6. So what comes next would be a 4s1. Now this is much higher in energy, so that's why this is not going to form in any kind of regular sense or form within anything that would be a stable compound. So this would be a really high energy atom and would really easily lose that electron if it were actually able to ever absorb it in the first place. Electron affinity is the energy that accompanies adding an electron to an atom. So if we go to chlorine absorbing an electron to go to chlorine minus, of course this is the gaseous atoms undergoing these conversions, that this is an exothermic reaction. The delta H, if you will, of this reaction is defined as the electron affinity of chlorine, and this is equal to about minus 349 kJs per mole. Key to point out here is exothermic, that it's more stable for chlorine to absorb the electron than for it to give it back. So if you think of chlorine losing the electron, that this reaction here, this would be the ionization energy of Cl minus. Now the ionization energy of chlorine would be chlorine losing electron to go to chlorine plus an electron. This would be the I1 of chlorine. The I1 of Cl minus would be equal to this reaction here. This would be plus 349 kJs per mole. Okay, so what this shows us is that chlorine is really holding on, chlorine ion is really holding on to that electron quite strongly. It would take energy to remove the electron. Energy is returned by adding the electron. So we start with chlorine up here, you add the electron in, and chlorine is more stable. So we make a more stable chlorine atom by absorbing an electron into it. So we get negative electron affinities, really negative electron affinities for like the halogens, not quite as negative for the oxygen group, and then a little bit more toward the positive side for the left side of the elements. Let's take a look at those trends. So our trends for electron affinity, surprisingly perhaps they're negative for the alkali metals, that it's relatively favorable for something like lithium or sodium to actually absorb an electron and go to like sodium minus. So this minus 53 for sodium would be the energy associated with a gaseous sodium absorbing an electron to go to sodium minus. Now, I wouldn't get too excited about this being negative because this is still never really going to happen in nature, because it will always end up being more favorable for sodium to lose an electron to go to the plus, more favorable for chlorine to go to the minus. Like if you're thinking about sodium here in terms of, well, would this go plus minus? Why would it not go minus plus? Well, it's because it'll take a lot more energy for chlorine to lose an electron than sodium, and then you're not getting as much energy back when sodium absorbs the electron compared to when chlorine absorbs the electron. Okay, so it's always going to be more favorable to go this way and not that way, even though you do get a minus sign for the electron affinity of sodium. So now when you look at the electron affinities, they're mostly negative. Like if you look at 1A, 3A, 4A, 6A, and 7A, they're all negative. 8A is really easy to explain why these are all really positive. In fact, they're not exactly easy to study when they're positive. So we don't even see the exact values. So helium and the noble gases are all positive because this is putting electron into a higher subshell. So this would be, putting the extra electron into like a 2s1 or putting an electron into a 3s1. And there's just a tremendous energy associated with putting an electron into a higher energy subshell. Whereas if you look at all these other cases, they're putting the electrons into what is already being filled in terms of a subshell, or just in a slightly higher 2p subshell within the n equals 2 shell. Okay, so berylliums are positive. Like its groups are generally less negative than some of the other groups because you're putting the electrons instead of into a lower s orbital, but you're putting them into a higher p orbital. And so that for like something like beryllium, you have 2 electrons here, that 2p subshell, higher in energy if you want to add that extra electron. That difference in energy is why beryllium would be more positive than something like boron. Boron is just adding another electron to a p subshell, so not as much energy required to put an electron into what's already being filled in terms of a subshell. Carbon to nitrogen, or nitrogen is positive or not as negative as some of the other groups because you're then spin pairing. So you're spin pairing from nitrogen, so nitrogen would have NP3 configuration, and so then you're spin pairing that extra electron, so you get that spin repulsion of the added electron. So generally negative, it becomes more favorable towards the halogens. You restart with the noble gases being unfavorable because you're putting electrons into a higher subshell, not as favorable for 2A because you're putting electrons into the higher energy P subshell, and then not as favorable for the 5A group because you're spin pairing. So this is due to spin pairing. This is due to a higher energy subshell for the 2A, and then the noble gases is higher due to putting them into a higher shell. Okay, so that's roughly the first half of Chapter 7. We'll obviously discuss more examples in lecture and talk more about these ideas in class. Thank you for the attention.